we looked at stuff like q bar q, chi bar chi. For vector vector, we looked at stuff like q bar q, gamma mu q, chi bar gamma mu, sorry about this, chi. And for axial axial, we had q bar gamma mu gamma 5 q, chi bar gamma mu gamma 5 chi. So we did this case. And in this case, the scalar, we had to do some fiddling with first hadronic physics, then nuclear physics, to convert this quark level interaction, and also the gluon term, but we had to convert this quark level interaction to an interaction with nuclei. And we did that, and ultimately the scattering cross-section of a nucleus, the differential scattering cross-section of a nucleus for the scalar case, was given by, let me find this, the 2m, sorry, the 2mn. There was a form factor to account for the loss of coherence. And the other piece that we have is simply, kappa squared over 4 pi, 1 over v squared, times something that essentially just counts the nucleons, Fn, that counts the number of protons and the number of neutrons within the target nucleus. In a lot of cases, you find that Fp is equal to Fn, in which case this thing just reduces to an A squared times Fp squared. And you see you can get a coherent enhancement of the scattering rate. And for that reason, we call the scalar-scalar reactions spin independent, because you don't care about the spin state of the target nucleus. You just care about how many nucleons it has and your relative couplings to each. So the next case I want to do is vector-vector. And the thing I want to remind you of is the expression for the electromagnetic current, the conserved electromagnetic current in terms of elementary fermion fields, is a sum over all fermions times the electric charge of each fermion times F bar gamma mu F. So when I sum over all the fermions in my theory, this operator corresponds to the charge density. So in other words, the zero component is the number density, and the spatial component is the charge current, the spatial charge current. And in particular, J0 is, you can think of this as a sum on fermions times the charge of the fermions times the number of fermions minus the number density of antifermions. Yes? So for the scalar case, there should also be a term involving gluon. Yes, yeah. But we saw that gluon term can be lumped into the effective coupling Fp or Fn. Okay. So the point with these vector-vector couplings is that this structure, this operator structure, is not quite exactly the charge current, but it's related to it. And we know that for the charge current, d mu electromagnetism is equal to 0 because electric charge is conserved. This is just a local charge conservation. And this picture has two results. The first result is that I think that the physical interpretation of this electromagnetic charge current is straightforward. And the electromagnetic current is just the sum over the individual number currents of all the charged fermions. So the total charge current is I count out all the individual fermions, multiply them by their charge, and that's my total electromagnetic current. So with this interpretation, we can say two things. The first thing we can say is that, I'll say this is thing number one. The first thing we can say for vector-vector is that chi mu gamma mu chi is actually, in fact, exactly 0 for Majorana. And the reason for this is a Majorana fermion is its own antiparticle, so I can't have a net asymmetry. And in particular, Majorana fermions can't carry electric charges. This means that this vector-vector interaction only applies to some kinds of dark matter. For example, in supersymmetry, your neutralino dark matter is a Majorana fermion. So this vector-vector coupling doesn't come up in that case. But there are other theories of dark matter where you can have Dirac fermion dark matter. The second thing is that on the quark operator side, 2, 2, the Q bar gamma mu Q, I can think of this as the current density, J mu Q, of this type of quark. And when I say quark density, I mean the net quark density in the sense of number of quarks versus antiquarks. So the upshot of this is if I apply number 2 to nuclei, my proton and my neutron, my proton in terms of its net quantum numbers corresponds to UUD. My neutron in terms of its net quantum numbers corresponds to UDD. And that means that I don't have to go through this funny business to relate the coupling at the VV level to the coupling at the nucleon level. And the reason for that is that we know that these are the net quantum numbers of the proton and the neutron. And this operator is just counting that. So that means that, where should we go? That means that if I think about something like a nucleon operator with Q bar gamma mu Q n, this just corresponds to the net number of Q in that nucleon. So the upshot of all that is instead of going through this business where for the scalar-scalar interaction, we had some complicated F, T, Q, N, whatever, we don't have to do that in this case. If we start off with the effective Lagrangian, if we start off with the Lagrangian of, I want to call it BQ, Q bar, gamma mu Q, chi bar, gamma mu Q. If I start off with this Lagrangian, my effective Lagrangian at the level of nucleons is just going to be an Fn, n bar, gamma mu n, chi bar, gamma mu q, plus Fp, chi bar, gamma mu chi, I forget, p bar, gamma mu p. So this is just like what we did with the scalar-scalar interaction, but now we have gammas between these fermion fields. But in this case, we have an easy relation between Fn and Fp with the underlying quark interactions. So for the Fn case, what we have is this is just 2 Bu plus Bd, and this is just Bu plus 2 Bd. So the reason for these simple relations corresponds to this fact too, that this operator just counts a net number of quarks in these nucleons, and for the proton or the neutron, we know the net nucleon number, so the net quark numbers, UUD or UDD, and that just corresponds to the fact that I have 2 up quarks here, 2 times Bu plus Bd. So do you have a question?
I guess the number that operator is the 0th complement of that.
Yeah. So when I'm talking about the number, it's secretly the current, because yeah, remember it's actually the 0 component that's the number operator, but this is just the relativistic generalization. So for example, I could sit in the rest frame where I have J0, no current, and then just boost to whatever. So this is a nice relation. I don't have any funny non-perturbative stuff. I just have a very simple relation between the underlying quark level operators. So I should be summing this over all the quarks in the theory. And this is what I get at the end of the day. And 2 other things is there's no contribution from heavy quarks. And the reason there's no contribution from heavy quarks is there may still be some net, or some overall quark content of heavy quarks in nucleon. But you have, on the average, equal numbers of quark-antiquark pairs. So you can think of the heavy quark content of a hadron as being sort of bubbles of quark-antiquark pairs. You don't have any net quantum numbers of them. The only net quantum numbers you have are UUD or UDD, and that translates into this. So in this sense, maybe I should have done vector-vector first, but in this sense, the vector-vector interaction is simpler than the scalar-scalar because I have this easy relation between the effective neutron and proton couplings and the underlying quark level couplings. Whereas we had to do this song and dance for the scalar-scalar. Okay, so we have that effective interaction. And it turns out that when you sit down and you take this effective interaction and compute the nucleon level cross-section, you just get the same result, at least a momentum transfer that you did for the scalar-scalar case. You just get a 1 over 4 pi. There's no kappa squared because kappa has to be equal to 1 because it's Dirac. So this is a single nucleon result. And then to convert the single nucleon result to the nuclear result, we use the same trick, d sigma n dq squared at q squared equal to 0 times the form factor. And as far as this guy goes, this guy gets coherent contributions from each of the nucleons. So this guy is just 1 over 4 pi, 1 over v squared, and I have the same z fp plus a minus z fn all squared as before, because in this case, I'm just counting protons and neutrons. So this is going through again. And it turns out that this form factor, where are we? This form factor, we can use the same form factor as for the scalar-scalar case. So the scalar-scalar form factor is actually based on the total nucleon number, whereas this one is actually related to the charge density. But typically in nuclei, we expect the charge density to track the mass density. And the upshot of that is that because the charge density is tracking the mass density, this same form factor, as for the scalar-scalar that tracks the mass density, also works for the vector-vector. So this is the story for the vector-vector interaction. It's straightforward, and it goes through very much like the scalar case. It's even easier because we don't have to play non-perturbative games. Okay. Actually, let me just say one. Let me just make one additional point, and that is that if I look at this operator, this operator is a bit of a cheat. This operator is a bit of a cheat because if I split my quark operator into left and right-handed bits, remember my 4-component Dirac quark field has a 2-component left-handed piece and a 2-component right-handed piece. And in the weak interaction, the weak vector bosons couple differently to the left and right-handed pieces. And this corresponds to the fact that, for example, if I look at how the Z vector boson couples, you can show that Q bar gamma mu Q can be split into Q bar left, gamma mu Q left, plus Q bar right, gamma mu Q right, where these Q lefts and Q rights, you can think of them as 4-component objects with just Q left here and 0, or Q right here and here. And in my effective interaction for the vector-vector case, I assumed implicitly by writing my effective operator this way that I had q bar left, gamma mu q left, or q bar right, gamma mu q right. But in principle, what I could have instead of just a single BQ, what I should really have in more generality is BQ left, q bar, gamma mu q left, plus BQ right, q bar right, gamma mu q right, and then this whole thing connects with chi bar gamma mu chi. And the way to handle this stuff is that the net BU that you plug into here is just the sum of the left and right-handed pieces. So when you can think of this as just writing a net BU at the end of the day as being BU left plus BU right, and similarly for BD. So the reason I'm mentioning this is that the most common, or at least for WIMP dark matter, that happens to be Dirac, this operator, this vector-vector operator, typically comes from a Z exchange. And I'll just erase over here. The Z exchange is going to look something like this. I'll put my Q's here, Q here, Q here. My Z exchange like this. Again, at low momentum transfer, I can shrink this to a point. But it turns out that the effective Z coupling to left and right-handed guys can be different. So the effective Z coupling to left-handed guys, in general, the Z coupling goes like T3 minus Q sine squared theta W. So this is the electric charge, this is the weak mixing angle, and this is the SU2 part. So this T3 is equal to either plus or minus 1/2, or for left-handed guys, and 0 for right-handed guys. So all that I'm getting at is the effective coupling at this vertex can be different for left and right-handed fermions. And for this canonical Z case, you actually have independent left and right-handed contributions. So I'm just mentioning this. Should you try to, if you want to work out the effective Z contribution to a VV operator, you actually have to take into account the independent left and right-handed pieces, and it's not just a universal quark coupling. So this is all I want to say about vector-vector, and I want to move next onto the axial-axial case, which is going to turn out to be spin-dependent. And we're going to have to jump through a few hoops to get to it, but it's going to go through very much like the scalar-scalar case. So for the axial-axial case, we're going to find that the effective coupling can be related to the spin operator acting on nucleons and nuclei. And the first thing we need to do is just like the first thing we did for the scalar case, we need to look at what the matrix element of an outgoing nucleon field with momentum P4 looks like with this operator in between. Because this is the thing we're going to use if we want to compute scattering induced by this operator for a nucleon and a nucleon. So this is going to be the nucleon side of the matrix element for dark matter scattering with a single nucleon. So the picture is this, and then I have nucleon here, dark matter. And it turns out that at low momentum transfer, what you get for this is given by just some overall number that I'm going to call delta Qn times a Dirac spinner and an S mu. And this S mu, I'll get to in a second, but it corresponds to the nucleon spin operator. Now, this nucleon spin operator at this level, I've written it in a Lorentz invariant form. But in the non-relativistic limit, where the momentum transfer between the two nucleons is very small, when the momentum transfer is very small, this non-relativistic limit, this S mu is approximately equal to 0, J, where J is just this familiar total spin operator you've seen in quantum mechanics. Okay, so we have this result, and this is just some number. This is something that starts to look like what you would usually compute in a matrix element, but you do have to worry about the spin here. So this is the first point. Now, given this result, we can rewrite our effective interaction in terms of quarks as an effective. We can rewrite our quark interaction as an effective interaction between nucleons in the form of. So suppose we start off with my Lagrangian interaction given by the form of a sum on quarks, q bar gamma mu q, gamma 5 q, chi bar gamma mu gamma 5 chi times an effective coupling that I'm going to call AQ. Given this quark level interaction, we can convert this into a nucleon level interaction using this matrix element result. And the corresponding effective Lagrangian, and this goes through in exactly the same way as what we did for the scalar-scalar case, this effective Lagrangian, which at low momentum transfer reproduces the effect of this quark level operator as a nucleon level operator, is given by, we write this, there's a proton piece, chi bar gamma mu gamma 5 chi proton S mu proton plus 2 root 2 GF. So I'll get to defining the intermediate stuff in a second. Chi n bar spin operator n. So I'll get to. Oh, and I forgot my. Sorry, I forgot to write the coupling. So I'll give you what the AP and the ANs are in a second. But the point is that if I compute with this effective Lagrangian, treating the protons as elementary fermion fields, I would get the same scattering matrix element. I would get the same result as this, computing with this effective Lagrangian, as I would from the quark level thing. Because, for example, let's say I had an n, p4, n bar, s mu n, n of p2. If I treat my nucleon as a fundamental fermion, I would just contract up these guys, and I contract up these guys, and I'd be left with this structure in between, and I would just get a u bar 4, S mu U2. So the whole point is this effective nucleon level interaction reproduces the interaction that I would get from this quark level matrix element, at least at low momenta. So this is my effective low energy interaction that at this point, instead of treating my protons and neutrons as composite objects, at this level I'm treating them as elementary objects. Yes?
The 1, 2, 3 components are basically the commutator of gamma 1 to 3.
Yeah. Well, so I haven't tried to define this S mu in general. We're always going to take the non-relativistic limit, so we're always going to work in a limit where we only care about the spatial pieces. In the relativistic limit, relating, I guess, if you think about boosting a system, boosts and rotations get mixed up, and that means that the notion of spin gets mixed up when we look at it in the relativistic case. But in the non-relativistic limit, this operator reduces to the spin operator, And for the non-relativistic object, I can identify spin essentially in the usual way. So we're always going to look at the non-relativistic limit because the typical dark matter velocity coming in is pretty small. Sorry. Another question? Yes. Yeah. Sorry? But it's a total. It has everything. So spin and orbital. Okay, so this is my effective Lagrangian, and I didn't tell you what these ANs and APs are, but it's not hard to sit down and sort them out from this result. Okay, well, so I'm just going to write AN, and N can now be N or P. And this has contributions from up, down, and strange quarks. And it just gets a net contribution from each of the individual quark operators. I have a root 2 GF, delta QN. So just to tell you what's going on, this GF is Fermi's constant. This is the constant with dimensions of 1 over mass squared. And you can write the weak interactions, the effect of weak interactions at low energies in terms of the Fermi constant. So you can think of the Fermi constant as characterizing the strength of weak interactions at low energy. And what I've done here is I've just multiplied by GF and divided off by it in the definition of the ANs. So I don't have to do this, but it's traditional. And the reason it's slightly useful is that, remember that this thing has dimensions of 1 over mass squared, and this thing also has dimensions of 1 over mass squared. So this thing normalizes into something that's dimensionless. And these delta Qs are things that you can't compute. These delta Qs are things that you have to compute, you have to get by doing some sort of hadronic physics or lattice QCD or chiral perturbation theory. So these things are just numbers that you go and look up. They're not things you can calculate in perturbation theory. But all I've done here is I've taken my effective Lagrangian, where I have contributions from each of the individual quarks. I've used in this result that the quark, because the nucleons contain quarks, this quark operator can connect a nucleon with a nucleon and induce the scattering. And I've turned the effective nucleon interaction into an effective, the effective quark interaction into an effective nucleon level interaction, where at this level, because the momentum transfer is small, I don't probe the internal structure of the nucleons, and I can think of these as fundamental fields. So this is another example of what's very common in quantum field theory, and actually in a lot of other areas of physics, where it doesn't make sense to carry around the full microscopic structure. Your life can be much easier if you zoom out and describe your system in terms of the degrees of freedom you actually have access to. Yes?
You said delta Q was computed using numerics?
Lattice QCD, where you essentially do a numerical simulation of QCD to connect the underlying quark dynamics into a bound state nucleon. It's not something you can do in perturbation theory. I stand corrected. I think it's even worse than that. I think it's actually usually extracted from data, where you look at scattering spin polarized beams on nucleons, for example. But in any case, it's not something, just think of it as a number that you look up. Okay, so at this level, we can go through and do something very similar to what we did in the in the scalar case, but we have to be a little bit more careful. And the reason why we have to be a little bit more careful is now, instead of just having an n bar n here, which would correspond to a mass density operator at the level of nuclei, we instead have this thing which is related to spin. So we need to take into account the spin dynamics. Okay, so the next step is converting. These nucleon level operators with protons and neutrons into something for nuclei. And for here, for this we have to connect a little bit with nuclear physics. Don't worry, I won't get too much into it. But this object, we define this to be the matrix element between an outgoing nucleus with n bar s mu n n. So if I take this operator and I plunk it between two nuclear matrix elements, so this is the nucleus with lots of nucleons in it, and this is going to be this is a nucleon operator. We know that nuclei contain nucleons, so this matrix element is going to give me something non-zero, and this object is let me see here. This object is given a name called S mu n, and the interpretation of this is the contribution of this kind of nucleon, either a proton or neutron, to the total spin of the whole nucleus. So for example, in some kinds of nuclei, you can think of all of the nucleons within them as being paired up, and those paired nucleons tend to have canceling spins. But you might have one unpaired nucleon within the whole nucleus with an unpaired spin, and the total spin of the nucleus comes from that single unpaired nucleon, and that would pop out in terms of these operators. So that's the first step. It also turns out that what we really want is the total contribution both from neutrons and protons to the whole nucleus. And as far as that goes, you can show, this follows from the Wigner-Eckardt theorem, I won't go into it, that this combination, this is what we're going to want eventually. You can relate this contribution to an effective, to some number times an S mu n, where this S mu is the nuclear spin operator. So just to distinguish between this S, so maybe I'll put a tilde on. The tilde on the nuclear spin operator, the interpretation of this is very much like the S mu we had before. But now this S tilde of mu applies at the level of the total spin of the whole nucleus. Whereas this S mu is the nucleon spin operator. And the point is that this is just some Dirac structure that fits between two fermions. Whereas this thing, my total nucleus might be a fermion or a boson, depending on the net total number of nucleons in it. And this operator is some effective, some different nucleus level operator that's different from this S mu. Yes?
So the ket big N, that's not just a multi-particle state in a Fock space, right? It's much more complicated. That is created by, say, the N piece. So, we get a Fock space by
of individual nucleons. Yeah. So here, so think of this state as representing just the whole nucleus outgoing with some spin state. So I have some initial. I have my nucleus with some initial spin state that I'll label by J and M, and then I have some outgoing nuclear spin state that has to have the same J, but it has some M prime.
I understand that, but what I'm trying to say is, how do I understand this in terms of mathematics of quantum mechanics? Like, how do I actually go about creating such a state mathematically using the operators in the state? Or that's
yeah. Well, so what's happening is I'm actually going from one theory to a different theory.
right.
So I'm going from one effective theory to a different effective theory. So at the level of this theory, I'm treating my nucleus as an elementary object.
Okay.
Just with some total spin. It's some elementary object just with some total spin state.
Okay.
I'm not worrying about the fact that it's now made of nucleons. The connection with the fact that it's made of nucleons comes from this level. So at this level, I'm connecting my theory of a nucleus thought of as a composite state to these nucleon operators. Whereas here, I'm just treating the nucleus as some grand object. I'm not worrying about its substructure other than it's J and M. I've done essentially the same thing over here, where my nucleon is composed of quarks and possibly other stuff. But my nucleon is composed of quarks, and I've related my quark level operators to an effective nucleon level operator, where now my nucleon is treated as an elementary object. So I've just done the same step at a higher level over here. But the upshot of all this is that in the non-relativistic limit, this will just reduce to a spin operator. And the operations you're going to do on this piece are just going to be your familiar quantum mechanical operations. There's going to be one twist because in field theory, it turns out that you normalize your states a bit differently than in regular quantum mechanics. It turns out in field theory, we use a relativistic normalization where essentially the inner product goes to twice the energy rather than unity. But aside from that, this thing is going to be exactly like what you do in regular one-particle quantum mechanics. And we'll get to this a bit later on. But the upshot of this is that when we take our nucleus and we stick our effective Lagrangian between it, we're going to get one contribution from the protons, one contribution from the neutrons, and that contribution is going to take this form. And what I'm going to have at the end of the day from this is my matrix element for Q, and here I have a nucleus. And at this level, I'm treating my nucleus as not a composite object, but just an elementary object coming in and going out, possibly with a different spin state. This is going to have some net matrix element. And this matrix element is going to have a piece from the chi's. And the chi piece, if I label this as P3, and I label this as P1, P2, P4, this piece is going to reduce to just U bar 3, gamma mu, gamma 5, U1 from this usual part. And then on this side, I'm going to have some numbers corresponding to the prefactors over there. Actually, it'll just be a 2 root 2 GF. But then I'm going to have this lambda. And then I'm going to have this n tilde mu, n. And I'm going to have to worry about the spin states here. But the point is that I've gone from essentially a quark level description to a nucleon level description to a nucleus level description. And I'm able to compute the scattering matrix element in the same way I would if the nucleus was just an elementary object. Because the energies are typically low compared to the nucleus structure, I can treat it approximately as an elementary object, and I get to this level. So this level is starting to look like stuff I know how to deal with, and then I can just take the square and sum over the spin states, and this will give me the scattering matrix element, which is what I ultimately want. Now, it's going to turn out that this Sn and this Sp will also be numbers that that you're going to extract from typically from measurements. So let me just check this out. So I wrote down this lambda coupling, and given the result of, actually, sorry, let me just bring this down. Sorry, I'm changing my mind. So given this result, you can sit down and compute. And given this result, you can compute, at least at zero momentum transfer, the total nucleus scattering cross-section matrix element, d sigma n dq squared, at q squared equals to 0. I'll come back to q squared non-zero in a second. And remember, q squared is a momentum transfer. What you get from this result turns out to just be a 2 kappa squared over pi gf squared over v squared lambda squared j plus 1. So once we've gotten to this level, we can treat this in our usual quantum mechanical techniques. And you'll go over this in a tutorial. We can treat this using our usual Dirac traces, which you should be familiar with that. And at the end of the day, what you find when you plug this into your cross-section formula, you just get this result, at least at zero momentum transfer. And the spin sum here is going to give me a j plus 1. And everything else gets squared. And I've got the GFs and this and that. So I still have to figure out what this lambda is. But aside from that, this procedure is straightforward. It's basically just a generalization of the scattering you've done in field theory. So the one thing I need to go back and specify and figure out how to get is this lambda. So that's my next step. Okay. So the point is that we defined our lambda effectively between the relation between the spin content of the nucleus, this sp mu, and from protons and neutrons, and the sum of these two things is going to be proportional to the total nuclear spin operator between nuclear states. This is the only thing it possibly can be proportional to, based on how it transforms. But there's some constant of proportionality, and the constant of proportionality is lambda. And then and the problem now is, what is this lambda? So to get at lambda, to get at lambda, the first thing we do is recall that S tilde of mu reduces to just 0, and the total nuclear spin as 0 momentum transfer. So if we look at it at the limit of 0 momentum transfer, and suppose we take both sides of this relation, the AP S mu P, AN S mu N, is equal to lambda. This applies for any nuclear spin state. But let's evaluate both sides when the nuclear spin has the highest possible J. So we assume the nuclear state has a net total angular momentum of J. And then, of course, it's going to have different values of M, of minus J plus 1, all the way up to plus J. So let's evaluate both sides when the nuclear state corresponds to the state with net J and when it has M equals to J. OK, so the first thing is that one defines the quantities Sp, and similarly for Sn, as being the nuclear state with the highest magnetic quantum number, J, of the Z component of this S mu operator. So one defines this quantity Sp to be this operator, where this Sp of Z is just P S mu P, with mu equals 3 equals Z. So in other words, I'm just taking the definition of S mu N, and I have N bar S mu N. I'm taking the third component, so the Z component of that, and I call the Z component of that Sp. But and the physical interpretation of this is within this nuclear state. What's the contribution to the total? What's the contribution to the total magnetic quantum number from protons? So it's a fractional proton contribution to the total thing. And then I can do the same thing for Sn. And it turns out that these are numbers that are obtained from experiments. So these are just numbers you look up. They're not things you can really compute from first principles unless you do either hard nuclear physics or experiments. So you can go and look up these Sp and Sn numbers. It's just the relative contributions of protons and neutrons to the net spin in this state. But on the other hand, as far as the right-hand side goes, where we have lambda, so this is going to give us our left-hand side. Our right-hand side is going to be lambda times, I'm going to have my nucleus in state Jj. And here I'm going to have, again, S mu equals 3. But now this is the total nuclear spin operator, Jj. But this total nuclear spin operator for mu equals 3 equals J is just Jz, my happy nuclear thing. So this Jz between this state and this state just gives me a J. So this side is just equal to lambda J. And now if I set left-hand side equal to right-hand side, this tells me what my lambda is. So left side equals to right side for this particular state tells me that my lambda is equal to 1 over j AP SP plus AN SN. So now going back to my starting point, remember my starting point was some, have I erased my starting point? My starting point is over here. My starting point is some effective quark level couplings between dark matter and quarks. And my first step is to relate this to nucleon couplings. So my nucleon coupling level of stuff, the only thing I get is some delta Q coefficients. And these delta Qs are things that, as far as we're concerned, we just look up. So that means that once we look these up, we know what our ANs are for n equals P and N. And now we've played this spin dance. And the spin dance means that we look up this number and this number as well. We know what this is. We look up this and this. So we know what this whole thing is. This is the total J of the nucleus. And now that we have lambda, we're basically done. Because we know what d sigma n dq squared is in this combination. So we now have our spin-dependent scattering matrix element at the level of a combination of numbers we have to look up that encompass the nuclear and hadronic physics. And we've already done the particle physics in the sense of we've taken our theory of dark matter to compute the AQs. And we've done the field theory computations to get at the scattering matrix elements. Now, there's one more thing we have to do. And that one more thing we have to do is generalize our q squared equals 0 result to q squared non-zero. So just get this down. So for the q squared equals to 0 result, we're just going to tack on a form factor. And while I'm at it, I'm going to convert d dq squared to a d dr. Remember, er is just q squared over 2mn. So this thing is just going to be 2mn times d sigma n dq squared at q squared equal to 0. And then at this point, we also tack on a form factor. And the form factor that we tack on is going to be, it's usually written as s of q squared divided by s of 0. So the s of 0 result is implicitly just the result we have at q squared equal to 0, which is what we know. It's just this lambda jj plus 1 AP junk. But at q squared equal to 0, the form factor has different pieces. The form factor has so the form factor in this case is a bit more complicated. And instead of just having one form factor function, there are actually three. There's a 0, 0, 0, 1, and 1, 1. And what I mean by 0, 0, 0, what I mean by 0, 1 is that this is AP plus AN. This is AP minus AN. And the reason why we split protons into this form and this form is that for nuclei, it turns out that there's a notion of isospin in nuclei where the isospin operation is an SU2 symmetry that flips protons and neutrons. So there's an idea of nuclear isospin, which is just an SU2 symmetry, or it's an SU2 that's an approximate symmetry of nuclei. And you have a doublet. You have a doublet with a proton and a neutron in it. And here we're combining proton and neutron stuff. And the point is this A0 corresponds to a singlet. And this corresponds to a triplet. under the nuclear isospin. And it turns out that for doing the nuclear physics calculations that go into finding S00, that go into finding these, this is a useful split. This is a useful factorization because it turns out that these pieces evolve independently. And is it just analogous to adding spins? 1/2, 1/2 gives me 0 and 1. The 1's a triplet. The 0's a singlet, and so on. OK, but in any case, these are also functions you go and look up. And the A0 and A1 are just things you know how to compute out of these things that you've computed already. Yes?
So could you remind me why we can do that factorization, or if that's the definition of the form factor?
I just defined this. This is just the definition of the form factor. So all this is doing, though, is it's taking the behavior of the thing at 0 momentum, and it's taking into account that spin kind of gets mixed up when I have non-zero momentum transfer. So when we talk about spin, strictly speaking, the spin only applies in the rest frame of that particle. So this just generalizes that. And again, these are things you look up from nuclear physics. OK, so I've gone through these different cases for calculating cross sections, and the whole game is that. In some sense, our underlying job to start off with is to come up with theories for dark matter. And once you have your theory for dark matter, you want to compare it with various experimental results. And these are the procedures you go through to compare with experiments. You find, in this case, your AQs. You then convert them into AN, AAP. And then you convert this into an effective scattering cross-section. And then you go and compare with experiments. So I've got a few more minutes. And the few minutes I have left, I want to start talking about what the current experimental state of dark matter searches are. Because there's actually a very interesting story. And I'll probably have to continue this in the next class, but let's go. So dark matter, direct detection, is current experimental status. And the current theoretical status is closely linked to the experimental status. So I'll talk about spin independent and spin dependent separately, because, again, the signals factorize into spin dependent and spin independent. And well, so first of all, in the case of spin-independent cross-sections, we see that we can get a very large enhancement for heavy targets. So typically, these experiments take heavy nuclei. And a very popular one is xenon, which has an atomic number of about 130. So you can get factors of 130 to the 4th for lighter dark matter. And you put limits on spin-independent cross-sections with that. But there are also other experiments with other target materials. And you want to compare these various different experiments with each other. And for that, in a sense, you want to factor out the dependence on the individual nucleus. And you just want to get a net effective cross-section per nucleon that lets you compare the results of one experiment to another experiment. So for that, one defines an effective spin-independent cross-section. You can think of this as an effective cross-section per target nucleon. And the way you define this is you divide off by a squared. You divide off by an effective nucleon mass divided by the nuclear mass. And then you take the effective cross-section here. So remember that for spin independent, sigma bar n was given by, let me just flip back. So for spin independent scattering, recall that we had, where I am. So in general, we had a d sigma der, or d sigma d squared that depended on q squared. But we define an effective cross-section, a cross-section with a bar, as just an integral over the full kinematic range, 4 mu n v squared dq squared of just d sigma dq squared, but specifically at q squared equal to 0. So this isn't actually the total cross-section. We've gotten rid of the form factor, and we've just taken the 0 momentum result. But this result for spin independent was just kappa squared over pi mu n squared zfp plus a minus z fn all squared. So the point of this effective per nucleon cross-section is that we divide off by a squared. And dividing off by a squared essentially normalizes this by the enhancement from the coherence. And we also replace the mu n squared that depends on the specific target mass by the reduced mass of the dark matter proton system. So the point is that we're factoring off. This is the thing you actually limit in the experiment, but you can recast the limits on this as limits on this effective spin independent cross-section. OK. And I should also mention that for many of these limits, implicitly they assume that fp is equal to fn. But this definition doesn't necessarily depend on that. But in any case, the current limits on this look something like this. So they're plotted as a function of the dark matter mass in GeV versus this effective sigma SI, which people do it in different units, but I like to use centimeters squared, because remember, it has cross sections have units of area. So the effective limits on this quantity look something like this. So this is about 50 GeV. They start to fall off towards 10 GeV, and going out to 100 GeV, and they start to get a little bit weaker. So the current limits mean that everything sort of through here is ruled out. So the current limits rule out effective spin independent cross sections for dark matter masses in this 100 GeV range down to values of something like this is close to 10 to the minus 45 centimeters squared. And by the time you hit 10, this is more like 10 to the minus 40 or so. So the current limits on dark matter direct detection are ruling out all this region. And these limits, the shape of the excluded region, it's best here, and it falls off over here, and it falls also over here for two different reasons. So in this region over here, your limit is getting a little bit weaker. And the reason for this is that remember that d sigma n, der, sorry, not d sigma n, the total rate as a function of the recoil energy, remember that this was proportional to the local dark matter flux. And the local dark matter flux is proportional to the local dark matter energy density divided by the dark matter mass. So in other words, the local dark matter flux is proportional to the local dark matter number density. But the thing we limit based on gravitational physics is this energy density, which is just m chi times the number density. And this thing is something like 0.4 GeV per cubic centimeter. So the point is that this rate, the effective limit you get once you fix this, the limit on the cross-section falls off for larger masses just because the number density gets smaller. So the thing you know is the total energy density. So the heavier the mass, the smaller number of dark matter particles you need to make up that total density in energy. And that means you get a fall off over here from the fact that you just have fewer dark matter particles around. You have a smaller dark matter number density and correspondingly a smaller dark matter flux. On the other hand, the reason you fall off quickly on this side is slightly different. On this side, what's happening is that most of these experiments use very heavy target nuclei. So the strongest limit comes from an experiment called xenon 100. And the target nucleus of xenon 100, as you might expect, is xenon. And xenon has an atomic number of about 130. So that means that a single xenon nucleus has a mass of about 130 GeV. On the other hand, remember that our momentum transfer is something like 2 mu n v cos theta. So our momentum transfer can only be as large as 2 mu n times v. Our typical v is like 10 to the minus 3. And what happens for very large for very large mu n, this large mu n goes like it goes roughly like m chi for heavy nuclei. And what ends up happening is that for lighter dark matter particles, your momentum transfer gets smaller. And the detectors that look for this nuclear scattering, this momentum transfer, lose sensitivity very quickly at low momentum transfer. So remember, your ER is proportional to q squared, which is going to be proportional to m chi squared. So this means that as a dark matter mass gets smaller, the recoil energy gets smaller very quickly. And the detector sensitivities turn out to essentially have a lower limit on recoil energies of a sort of order 10 keV, depending on the specifics. So what's happening over here is that the recoil energy is getting smaller, and the detectors just lose sensitivity to the dark matter scattering as a material effect. So the detectors just aren't sensitive out here, so you're not sensitive to very light dark matter. So I'll come back tomorrow and talk a bit more about the current situation, but the puzzle is that these are the results essentially of the xenon 100 experiment. But there are also other experiments looking for dark matter that seem to have an excess above their expected backgrounds. And when you try to interpret that excess in terms of dark matter scattering, the regions it seems to prefer kind of live up around here. So there's obviously some kind of problem in that some experiments seem to have a signal that's in a region that seems to be ruled out by other experiments. So this is a bit of a puzzle, but there are also interesting interpretations, and I'll get to that tomorrow.